In this video, we're going to be looking at integration by parts. Okay, so here at the top, I've shown a differentiation, which you should be familiar with. It's simply just a chain rule. E to the fx differentiates to e to the fx, but f dash x also multiplies at the front. Okay, so below here, I've got 3 examples, and I want you to look at them and tell me on which one of these can you use the reverse of this rule to integrate. Okay, so the third one is perfect because e's power is sine x. In front of it, the differentiation of sine x is multiplying. You've got cos x there. So it's in the form f dash x e to the fx. So it simply integrates to e to the fx, which would be e to the sine x. Now the second one is not too bad also. As e's power is x squared, what we have at the front is x. And the differentiation of x squared is 2x. So although it's not perfectly 2x at the front, it is a multiple of it. So this one is also okay. You can use the reverse chain rule to integrate this one. However, if you look at the first one, we have a problem. E's power is x, and the differentiation of x is not at the front. And you wouldn't be able to use the reverse chain rule to integrate this one. You'll do well to think of something which differentiates to this off the top of your head. And for these types of questions, we have to use integration by parts. Generally, integration by parts usually happens when you have 2 functions timesing each other like this. But it's not a perfect rule because it's not always the case. And we might look at an example where it's not quite like this, but it ends up being integration by parts. So here's the formula for integration by parts, and you should memorize it. Let's look back at that question where we said we need to use by parts. X to the ex. Okay, so how does this formula work? Now, with integration by parts, we usually do it when 2 functions are multiplying each other. So what are the 2 functions here which are multiplying each other? It's x and ex. These are the 2 functions we're playing with. So to use this formula, you're going to choose one of them to be u and one of them to be dv dx. That's the key thing with integration by parts. Okay, so how are we going to choose? Who's going to be u and who's going to be dv dx? Now usually we let the part which is easier to differentiate be u, and the part which is easily integrated to be dv dx. So we're going to choose x to be u, and the ex can be dv dx. Okay, so to fill in the rest of the formula, we need to differentiate the u to get du dx, and we need to integrate the dv dx to get v. So x differentiates to 1, and dv dx integrates to v equals ex. That's brilliant. We've got all the parts for our formula, and we can just go ahead and fill it in. Now the left-hand side of the formula is simply just going to be the question. Now that we've filled in the formula, we've got an integration to do on the right-hand side. So let's go ahead and do that. Now this integration we should know how to do. It's simply integrating ex. And don't forget the c of integration. And we're done. It's as simple as that. So remember the key thing is let one of them be u and let one of them be dv dx. Then you differentiate the u and you integrate the dv dx, and you'll have the remaining parts of the formula. And you just go ahead and fill it in. And remember the key sign that you've got a by parts question is there's usually 2 functions multiplying each other. But I'd recommend that you check that you can do integration by recognition or any other patterns before you start using by parts. Before you do integration by parts, just double check that you can't integrate it by easier method. For example, integration by recognition. Okay, so let's try it on another question. So here we've got x squared ln x. And we don't see any of our recognition forms of integration. So it's probably going to be integration by parts. And you've got 2 functions multiplying each other. Okay, so who's going to be u and who's going to be dv dx? Now remember, we need to choose whatever's easy to differentiate to be u, and whichever is easy to integrate to be dv dx. Now it's very hard to integrate ln x, So we're going to let ln x be the u. And that's generally the case. We generally let ln x be u. And of course that lets x squared be dv dx. So we need to differentiate the u, and that gives us 1 over x. And integrating the dv dx gives us 1/3 x cubed. Now we simply just need to fill in the formula. So on the left hand side, it's just the question, so you don't need to think about filling in that part. Just rewrite the question. Then we have u times v minus the integration of v du dx. So we've still got an integration to do. Let's just tidy that up a little bit. And you should notice here I've taken out 1/3 in front of the integration sign. And you can always do that at constants, because constants don't affect your integration or differentiation. And now what we need to integrate to complete this is not too bad. It's just simply x squared. So let's go ahead and do that. And don't forget that c, the constant of integration. So I mentioned earlier that I'm going to show you an example where you don't have two functions timesing each other, which is usually what we're looking for when it's integration by parts, but it still ends up being integration by parts. It's the integration of ln x. Now integrating ln x is not easy, but as soon as you use by parts, it's not too bad. We let u be ln x, and we let 1 be dv dx. So go ahead and have a go at integrating ln x. And there we have it. I hope you found that video useful. Support us by liking, subscribing, and share this with your friends. And if you still got some more questions on anything, drop a post on our forum at examqa.com where you'll find your questions answered.